Namaste. Today, I was hoping we could do a deep dive into metals and nonmetals. It feels like such a crucial chapter, for board exams and definitely for competitive tests like UPSC and SSC. I'm really eager to get a crystal clear, sort of exam-oriented understanding, their properties, how they react, basically what makes them tick.
Excellent choice. Yes, metals and nonmetals. It isn't just another chapter, is it? It's really a foundational pillar of inorganic chemistry. We've touched upon elements and their basic classification back in Class IX, but today we're going to systematically, peel back the layers. We'll classify them based on their physical and chemical properties. We'll delve deep into their reactivity, how we actually extract them from the earth, and even the fascinating way they form compounds. This understanding is absolutely vital, not just for conceptual clarity, but for confidently tackling those direct questions and the tricky analytical problems that will inevitably pop up in your upcoming examinations. So our mission for this deep dive, let's say it's to extract every essential nugget, every aha moment. We want to ensure you're not just prepared, but, well, truly well armed for any question this chapter dares to throw at you. Okay, so let's unearth this fundamental concept. Right, let's begin our exploration by examining the physical properties. These often give us the first, most straightforward clues about how to group different substances. We'll consider a range of samples, think iron, copper, aluminium, magnesium, sodium, zinc, lead, just to see these properties in action. Okay, first stop. Metallic luster. You know that distinctive shine metals have.
Yeah, the shininess.
Exactly, that's metallic luster. In their pure state, metals possess this, well, beautiful shining surface. If you look at a fresh piece of iron or copper or aluminium, you'll immediately notice it. And here's a little tip. If a metal looks dull, often just rubbing it with sandpaper can bring back that shine.
Why is that? Just cleaning it?
Pretty much. It removes any thin, dull oxide layer that might have formed on the surface. The fundamental reason behind this characteristic glow, it's all thanks to the presence of free electrons on their surface. These electrons act like tiny mirrors, basically, reflecting light and giving metals that unmistakable metallic brilliance. Okay, next up, let's talk about hardness. Generally speaking, metals are indeed hard. They resist scratching, denting, deformation, However, this isn't a one-size-fits-all rule. Their hardness varies quite a bit from one metal to another. If you were to, say, pick up a piece of iron, then copper, then aluminium, you'd quickly notice that iron feels much more rigid. It's less easily scratched than aluminium, for instance. Now, while this general trend is important, you need to remember that the true test of understanding often lies in the exceptions to these rules. We'll get to those very soon. They're crucial.
Tutor, you mentioned metals are generally hard, but I seem to recall some exceptions. Are there specific metals that defy this rule?
You're absolutely right to point that out, yes. The exceptions are often where those competitive exam questions come from. They separate those who've truly grasped the concepts from those who've just, well, memorized a list. But before we dive into those intriguing deviations, let's quickly nail down a couple more general physical properties that metals famously possess. Okay. One of those fascinating properties is malleability.
Malleability, right?
This is the incredible ability of metals to be beaten into thin sheets without breaking. Imagine taking a solid block of iron or zinc, lead, copper, and hammering it. Instead of shattering into pieces like glass might, these metals will flatten and change shape. They form thin sheets. Gold and silver are the real superstars here. They are renowned as the most malleable metals. This is a common objective question, by the way.
Okay. Good to know.
And this property is exactly why we can craft so many everyday items, from the cooking utensils in your kitchen to the aluminum foil you wrap your roti in, and of course all that intricate gold and silver jewelry that requires such fine shaping. Closely related to malleability is ductility.
Okay, ductility.
This refers to a metal's capacity to be drawn out into thin wires. Think about the copper wires carrying electricity throughout your home, or maybe those delicate gold threads used in traditional zari work in India.
Right, I've seen those.
Gold, once again, takes the crown here. It's the most ductile metal, and here's an almost unbelievable fact, but it pops up in exams. You can draw a wire approximately 2 kilometers in length from just 1 single gram of gold.
Wow, 2 kilometers from 1 gram.
Incredible, isn't it? That's a favorite for objective questions. So the combination of malleability and ductility is precisely what makes metals so incredibly versatile. It allows them to be shaped and formed into countless useful objects for countless applications, everything from massive bridge structures down to microscopic electronic components. Now, let's consider their conductivity of heat. Metals are universally known as excellent conductors of heat, which is also why they typically boast high melting points. To visualize this, think of a simple experiment you might have seen. You clamp an aluminium or copper wire to a stand, right? Then you attach a small pin to its free end with a bit of wax. As you heat the wire near the clamped end, the heat swiftly travels along the metal.
Melts the wax.
Exactly. Melts the wax and the pin drops. A simple demonstration, but it elegantly illustrates their high thermal conductivity. For your competitive exams, it's worth remembering. Silver and copper stand out as the best conductors of heat, whereas metals like lead and mercury are comparatively poor conductors. This distinction matters.
Got it. Silver, copper best, lead, mercury poor.
Precisely. And this exceptional heat conduction is, of course, the very reason metals are indispensable for making cooking vessels. They distribute heat efficiently and evenly. Following heat conductivity, we have conductivity of electricity. There's no doubt about it. Metals are superb conductors of electricity. If you complete a simple circuit using any metal sample, a bulb will glow brightly. It signals the free flow of current. This property is absolutely fundamental to our modern electrical systems. It's also why you'll notice electric wires are coated, usually with materials like PVC or rubber.
For safety, right?
Absolutely. Those coatings are vital for insulation. They prevent direct contact with the conductive metal wire and ensure safety by stopping current leakage. And finally, for physical properties, let's touch upon sonority.
Sonority, the sound.
Exactly, the sound. Metals are described as sonorous if they produce a distinct, resonant ringing sound when struck hard. This property is quite familiar to us in daily life. It's precisely why, for example, those resounding school bells that mark the start or end of classes are traditionally made of metals. Their unique ability to vibrate and produce a clear, carrying sound makes them perfect for such signaling purposes.
Okay, that's a very thorough overview of metallic properties, Tudor. It covers a lot. But what about nonmetals? I imagine they must be quite different, right? Do they share any similar characteristics, or are they essentially the opposite?
Precisely. Your intuition is spot on. If metals are one side of the coin, nonmetals often represent the exact opposite. Let's explore how their physical properties stack up. When we talk about the physical properties of nonmetals, it's important to note right away that there are far fewer of them compared to metals in the periodic table. Common examples you'll encounter include carbon, sulfur, iodine, oxygen, hydrogen. Now, when it comes to their physical state at room temperature, most nonmetals are either solids, like carbon and sulfur, or gases, like oxygen and hydrogen. But here's a crucial exception you must remember for your exams. Bromine.
Bromine, the liquid one.
Exactly. Bromine is a liquid at room temperature, the only nonmetal to be so. Very important. Now, in stark contrast to metals, nonmetals generally do not exhibit metallic luster. They tend to be dull. Nor are they typically hard, malleable, ductile, or sonorous. Furthermore, they are generally poor conductors of both heat and electricity. They act more like insulators.
So nonmetals are essentially the opposite in terms of these physical properties. Pretty straightforward. But is that always the case, or are there any interesting exceptions, just like with metals? I seem to recall something about iodine and carbon being a bit different.
You're right on the money. Yes. This is exactly where the complexities lie, and often where the trickier exam questions originate. While these are general trends, there are some very important exceptions that we absolutely must commit to memory. They frequently appear in multiple-choice questions and conceptual problems. These exceptions really test your deeper understanding, you see. Let's list these important exceptions and allotropes. Okay, first for metals. While the general rule is solid at room temp, high melting points, we have some significant deviations. Mercury, the classic one. The only metal that exists as a liquid at room temperature, frequently tested.
Hg.
Gallium and cesium. These metals have surprisingly low melting points. So low, in fact, that if you just hold them in your palm, your body heat is enough to melt them.
Wow, really?
Yeah.
In your hand? Yep. Into a liquid pool. Quite amazing. Alkali metals. Lithium, sodium, potassium. Unlike the hard metals you usually think of, these are incredibly soft. So soft you can actually cut them with a simple knife.
Cut them with a knife. Like butter.
Almost. They also stand out for having very low densities and relatively low melting points compared to other metals. Very different. Now, for nonmetals, which generally lack luster and conductivity, we also find some fascinating outliers. Iodine. This is a nonmetal, yet it is distinctively lustrous. It has a shining, almost metallic appearance. Another classic exception for exams.
Okay, iodine is shiny. Got it.
Carbon. Carbon. This nonmetal is incredibly versatile. It can exist in different structural forms, which we call allotropes, and each allotrope of carbon exhibits unique properties that starkly contrast the general rules for nonmetals. Diamond, an allotrope of carbon. Diamond is not only the hardest natural substance known, completely defying the nonmetals or soft rule, but it also possesses incredibly high melting and boiling points.
Diamond, yes, very hard. Graphite, another common allotrope of carbon. Graphite is, surprisingly, a good conductor of electricity.
Graphite conducts electricity,
Yeah.
but it's a nonmetal.
Exactly. This is a crucial exception. Most nonmetals are insulators, but graphite conducts. It's famously used in pencil leads, that's why they call it lead, though it's graphite, and as electrodes in various electrical applications because of this conductivity. So, to wrap up this section, these exceptions powerfully demonstrate that we cannot classify elements solely based on physical properties. While they give us useful initial groupings, physical properties alone aren't definitive. They have too many exceptions. This limitation naturally leads us to the more fundamental and definitive classification. Chemical properties. It's in their chemical reactions where the true story of how elements interact really unfolds. That's what we'll get into next.
Right. Now let's move into the heart of the matter, the chemical properties. These provide a much clearer, much more fundamental way to distinguish between metals and nonmetals. We will systematically analyze how metals react with various common reagents. First up, let's explore their reaction with air, specifically oxygen. It's a fundamental interaction you see everywhere. Almost all metals readily combine with oxygen to form metal oxides.
The general reaction is quite simple to remember. Metal plus oxygen, metal oxide.
Okay, metal plus oxygen gives metal oxide.
Correct. For instance, when you heat copper in air, you'll observe it forming a black-colored substance. That's copper oxide. Aluminium also reacts with oxygen, forming aluminium oxide, which is a white solid you might be familiar with. Now, when we delve into the nature of metal oxides, most of them are basic in nature. Think of copper oxide reacting with hydrochloric acid. It acts just like a base, neutralizing the acid. However, and this is a critical concept, frequently tested in competitive exams, some metal oxides show a unique dual personality. These are known as amphoteric oxide.
Amphoteric, meaning both.
Exactly. They demonstrate both acidic and basic behavior, meaning they can react with acids as well as with bases to produce salts and water. The prime examples you absolutely must remember are aluminium oxide, aluro, and zinc oxide.
Alro and ZNO.
Okay. So, for example, aluminium oxide reacts with hydrochloric acid like a base, sure, but it also reacts with a strong base like sodium hydroxide, acting like an acid, to form sodium aluminate. This ability to act as both an acid and a base is a key distinguishing feature, very important for exams. Now, about solubility. While most metal oxides are insoluble in water, there are some very important exceptions that readily dissolve to form alkalis, strong bases. Sodium oxide and potassium oxide are two key examples. When they touch water, they react vigorously to form strong alkalis like sodium hydroxide, NaOH, and potassium hydroxide, KOH, respectively. It's also fascinating to observe the varying reactivity of metals towards oxygen. They certainly don't all react at the same rate or intensity. Metals such as potassium K and sodium Na are incredibly reactive. You might have seen videos.
Yes, they catch fire, right?
They do. If you leave them exposed to open air, they react so vigorously with oxygen that they actually catch fire almost immediately. This intense reactivity is precisely why they are specifically kept immersed in kerosene oil.
Ah, the kerosene storage. That question comes up a lot.
It does. It prevents accidental fires and protects them from both moisture and atmospheric oxygen. Mark it well. Other metals like magnesium, aluminium, zinc, and lead react differently. At ordinary temperatures, their surfaces get covered with a very thin, protective layer of oxide.
Like a shield.
Exactly like a shield. This oxide layer acts as a natural barrier, preventing the underlying metal from further oxidation and protecting it from corrosion. This protected layer can even be deliberately enhanced. Have you heard of anodizing for aluminium?
Vaguely. It makes it tougher.
Yes, and more resistant to corrosion. Anodizing involves forming a much thicker, more robust oxide layer on an aluminium article through an electrolytic process. This thicker layer significantly improves corrosion resistance and can even be dyed to give aluminium products an attractive finish. You see it on window frames, cookware.
Okay, that's a practical application.
Now, in contrast, think about iron. It doesn't readily burn on heating in its bulk form, like a nail. However, if you take finely divided iron filings and sprinkle them into a flame, they burn vigorously. Why?
More surface area exposed.
Precisely. Vastly increased surface area. Copper, CO, also doesn't burn, but when heated, its surface becomes coated with that characteristic black layer of copper oxide we mentioned earlier. And at the other end of the spectrum, very unreactive metals like silver, A, and gold, AU, They don't react with oxygen at all, even when subjected to very high temperatures. They just retain their luster. So, based just on these observations with oxygen, we can start to put together a preliminary reactivity order. Potassium and sodium are clearly the most reactive, then magnesium, less vigorous, then iron, then copper, with silver and gold way down at the least reactive end. This order will continue to build as we explore more reactions, see how it works.
Yes, it's like gathering evidence piece by piece. That was a very detailed explanation of reactions with oxygen, Tutor. It's clear how varied they are. What about reactions with water? Do all metals react similarly with water, or is there a spectrum of reactivity there too? Is it similar to oxygen?
Good question. And yes, just like with oxygen, metals exhibit a wide range of reactivity with water. This is another crucial piece of the puzzle for understanding the overall reactivity series. The general reaction when a metal reacts with water is typically metal plus water, metal oxide plus hydrogen gas.
Okay, same products mostly.
Yeah.
Metal, oxide, and hydrogen.
Right. And if the metal oxide produced happens to be soluble in water, it will then further dissolve to form a metal hydroxide. But the exact nature of the reaction, its vigor, the conditions required, cold water, hot water, or steam, and even whether it occurs at all, depends greatly on the metal's position in the reactivity series. Let's look at the variations based on reactivity. The most reactive metals, again, potassium and sodium. They react incredibly violently, even with cold water. The reaction is so intensely exothermic, releases so much heat that the evolved hydrogen gas immediately catches fire.
So fire with cold water.
Yes. For potassium, it's a swift, almost explosive reaction, often with a lilac flame. For sodium, a similar vigorous burst darting around the surface with a yellow flame. Another reason for the kerosene storage. Now, calcium, K, reacts less violently with cold water compared to sodium or potassium. While heat is still evolved, it's not enough for the hydrogen gas to catch fire. But a unique observation with calcium is that it starts floating on the water's surface. Any idea why?
Does it get lighter? No.
Yeah.
Maybe the hydrogen gas?
Spot on. The bubbles of hydrogen gas produced adhere to the surface of the calcium metal, effectively reducing its overall density and allowing it to float. Good observation for practicals. Magnesium, Mg, is interesting. It does not react with cold water at all. However, it reacts quite readily with hot water to form magnesium hydroxide and hydrogen gas. And similar to calcium, magnesium also starts floating due to the hydrogen gas bubble sticking to its surface. So hot water is needed for Mg metals like aluminium, Al, iron, S, and zinc. Zn show even lower reactivity with water. They do not react with either cold water or hot water. Their reaction only occurs with steam.
Only steam. So gaseous water at high temperature.
Correct. They react with steam to form the metal oxide and hydrogen gas. For example, passing steam over red-hot iron will produce iron oxide and hydrogen. This specific requirement for steam is important for distinguishing the reactivity. And finally, the least reactive metals, such as lead Pb, copper Ki, silver Ag, and gold Au, show absolutely no reaction with water. Regardless of its temperature or state cold, hot, or steam, they simply don't have the chemical drive to interact with water in that way. So from these water reactions, we can refine our reactivity order even further. Look, K Nakaya, all cold water, MDU needs hot water, Al, Fe, Zn needs steam, Pb, Q, Ag, A, no reaction at all.
Okay, that's a clear progression based on water conditions.
Exactly. This sequence is a vital piece of knowledge for predicting chemical behavior, especially for those objective type questions.
So the type of water, cold, hot, or steam, plays a big role in reactivity. That makes a lot of sense. But what about reactions with acids? I'm curious, does reacting with an acid always produce hydrogen gas? Or are there exceptions to that rule too? Seems like there are always exceptions.
You're anticipating a very important nuance, and yes, you're right, chemistry loves its exceptions. It's a concept competitive exams particularly love to test. Generally, yes, hydrogen gas is produced when metals react with dilute acids. However, there's a critical exception with nitric acid that you absolutely must know. The general reaction for metals with dilute acids is straightforward enough. Metal plus dilute acid, salt plus hydrogen gas.
Metal plus acid, natric salt plus hydrogen. Okay.
But, just as we saw with water, the reactivity varies significantly. If you took various metal samples, say magnesium, aluminium, zinc, iron, copper, and added them separately to dilute hydrochloric acid, HCl, you'd observe vastly different rates of bubble formation. Those bubbles are the hydrogen gas, of course. Their speed indicates the reaction rate. For example, magnesium Mg reacts most vigorously with dilute HCl. You'd see the fastest bubble formation, and the test tube would get quite warm. It's the most exothermic. The reactivity generally decreases as you go down the series. MgAl, Z, and Fe. You'd see fewer bubbles, slower reaction. In stark contrast, if you place copper, C, in dilute HCl, what would you observe?
Based on the water reaction, probably nothing.
Exactly. No bubbles, no change. Copper does not react with dilute HCl. This distinct behavior further helps us rank metals in terms of their reactivity with acids. Now, for that crucial exception with nitric acid, HNO, it's a frequently tested concept, so pay close attention. Hydrogen gas is not typically evolved when metals react with nitric acid. Why?
Is nitric acid different somehow?
It is. HNO is a strong oxidizing agent. Instead of simply displacing hydrogen like HCl does, it actually oxidizes the hydrogen gas H produced to water. In the process, the nitric acid itself gets reduced. It gains electrons, forming various nitrogen oxides like N-, NO, or NO. The exact product depends on the acid concentration and the metal's reactivity.
So it reacts with the hydrogen it produces. Wow.
Essentially, yes. It prevents the H as gas from escaping as gas. However, there's an important exception to the exception. You absolutely must remember this for your exams, especially for MCQs. Magnesium, Mg, and manganese, MRO. These are the only two common metals that do react with very dilute nitric acid to evolve hydrogen gas.
Only Mg and HN with very dilute HNO.
Correct. Very dilute. That specific detail is a common trap for students, so make a mental star next to it. And while we're on the topic of acids, it's worth mentioning aqua regia. Ever heard of it?
Aqua regia. Royal water. Sounds impressive.
It is. A fitting name because of its unique ability to dissolve noble metals like gold and platinum. It's a freshly prepared mixture of concentrated hydrochloric acid, HCl, and concentrated nitric acid, HNO, specifically in a 3.1 ratio. 3 parts concentrated HCl to 1 part concentrated HNO.
So a mixture of 2 strong acids.
Yes. And its unique property is that it can dissolve gold and platinum, even though neither of these strong acids can do so alone. Is quite remarkable. Aqua regia is a highly corrosive, fuming liquid, and its ability to dissolve these precious metals makes it highly significant in the jewelry industry and for recovery processes. A truly powerful chemical tool.
Aqua regia sounds incredibly potent and clearly important for something like jewelry making. But how do all these reactions we've discussed with oxygen, water, acids, how do they relate to a metal's ability to displace another metal from its salt solution? Does it all tie into a single concept?
This is exactly where the concept of the Reactivity Series truly comes together. It provides a powerful predictive tool. The reaction with solutions of other metal salts, commonly known as displacement reactions, is based on a very clear and fundamental principle. A more reactive metal can displace, essentially kick out, a less reactive metal from its compounds when they are in solution or molten form.
More reactive pushes out less reactive. Makes sense.
The general equation for such a reaction is beautifully simple. Metal A plus salt solution of B, salt solution of A plus metal B. This means if metal A is more reactive than metal B, it will essentially push metal B out of its salt solution and take its place. And metal B will then precipitate out, usually depositing as a free metal solid. Let's consider a classic illustrative example. This often comes up in practical exams or descriptions. Imagine you place a copper wire into an iron sulfate solution, which is usually pale green. And separately, you place an iron nail into a copper sulfate solution, which is distinctly blue. What do you think happens?
Based on earlier reactions, iron seems more reactive than copper. So maybe the iron nail reacts, but the copper wire doesn't.
Exactly right. After some time, you'd observe a distinct change only in the test tube with the iron nail in copper sulfate solution. The iron nail would get coated with a reddish-brown layer of copper metal, and the blue color of the copper sulfate solution would gradually fade as colorless iron sulfate is formed. In contrast, the copper wire in the iron sulfate solution would show absolutely no reaction, no change at all. This simple observation allows us to confidently infer that iron is more reactive than copper. It successfully displaced copper from its salt solution. The significance of these displacement reactions is profound. They provide excellent, often very visual evidence for the relative reactivity of metals. In many cases, they are much easier to observe and interpret for a wider range of metals compared to reactions with oxygen, water, or acids, which don't react with all metals, as we saw. If metal A displaces metal B from its solution, you can confidently conclude metal A is more reactive than metal B, period. This systematic observation forms the very empirical basis for constructing the reactivity series. And this finally brings us to the complete reactivity series, also sometimes called the activity series. This is a fundamental concept for your exams, a list you absolutely must memorize thoroughly. It's not optional, really. It's essentially a list of metals arranged in the precise order of their decreasing activities or reactivity. Let me list the detailed series for you, from the most reactive metal at the top to the least reactive at the bottom. Think of it as a ladder of reactivity. Potassium, K, the undisputed king of reactivity, most reactive. Sodium, Ne. Calcium, Se. Magnesium, Mg. Aluminium, Alt. Zinc, Zn, Aaron, Fv. Lead, Pb. Then we have hydrogen, H. Now, hydrogen isn't a metal, obviously.
Right. Why is it there then?
It's included here as a crucial reference point, specifically for acid reactions. Any metal listed above hydrogen in this series can displace hydrogen from dilute acids, like HCl or HEAO. Metals below hydrogen cannot. It's a key dividing line.
Ah, okay. That makes sense.
Copper, C, below hydrogen. Mercury, Hg. Silver, Ag. Gold, Au. Right down at the bottom. The least reactive metal on our common list. Platinum would be even lower, typically. Now, you can clearly see the direct correlation between this series and all the observations we made earlier with oxygen, water, and acids. It all fits together. For example, the metals at the very top, K, Ne, Ka, Mg, react violently or readily even with cold water. Those lower down, Al, Zn, Fe, require hot water or steam. Those below hydrogen don't react with water or dilute acids like Q, Ag, Au. And a more reactive metal, positioned higher in the series, will always displace a less reactive one from its salt solution, like Fe displacing Q. This series is your ultimate roadmap to understanding and predicting countless chemical reactions involving metals. Master this, and you'll unlock a huge chunk of this chapter. Seriously, memorize it. Okay, so we've seen what happens in these reactions, the physical clues, the chemical outcomes, the reactivity patterns. Now let's peel back another layer and understand the deeper why behind these reactions. What fundamentally drives metals and nonmetals to react the way they do? This takes us back to something you studied in Class IX. Electronic configurations, remember those?
Yes, the 281 stuff, KLM shells.
Exactly. Let's recall the core concept of electronic configuration and reactivity. We know that noble gases, helium, He, neon, Ne, argon, Rr, are famously unreactive or stable. Chemically inert, we say. Why?
They have a full outer shell.
Precisely. They have a completely filled valence shell. Their outermost electron shell is full. 2 for helium, 8 for neon and argon. They're perfectly content, electronically speaking. They have no tendency to lose, gain, or share electrons. Now, the fundamental driver of reactivity for any other element, whether metal or nonmetal, is its inherent tendency to attain this stable, completely filled valence shell configuration, usually an octet 8 electrons in the outermost shell. It's like their chemical goal or aspiration. Let's take some classic examples to illustrate this drive for stability. Consider sodium. Its atomic number is 11. Its electronic configuration is 2, 8, 1.
Right.
K shell 2, L shell 8, M shell 1.
Right. 1 electron in the outermost shell.
Exactly. It has just 1 electron in its outermost M shell. Now, to achieve a stable octet, what's easier for sodium? Gain 7 more electrons or lose that one?
Lose the 1, definitely.
Absolutely. It's much, much easier for sodium to simply lose this single valence electron. When it does, its L shell, which now has a full 8 electrons configuration, becomes 2, 8, becomes the new stable outermost octet. In this process, the sodium atom loses 1 negative charge, the electron, but retains all its 11 positive protons in the nucleus. The result, a net positive charge of +1. It forms a positively charged sodium capsule written as a Na. Now, on the flip side, let's look at chlorine. Cl, atomic number 17, its electronic configuration is 287, K2L8M7.
7 in the outer shell, so it needs 1 more.
Exactly. Chlorine has 7 electrons in its outermost shell. To complete its octet and achieve that coveted stability, it needs to gain just 1 more electron. Much easier than losing 7. This inherent drive for stability in both sodium and chlorine brings us perfectly to the formation of ionic electrovalent compounds. When sodium and chlorine react, it's a perfect chemical match. The electron readily lost by sodium is eagerly taken up by chlorine. It's a transfer. So we have sodium giving up its electron, NaUe or R2, Ru. Its configuration changes from 2008 Meval 1 to a stable 2 Velar 8. Simultaneously, chlorine accepts that electron, Cl plus EOO. Its configuration transforms from 2008-87 to a stable 2008.
So sodium becomes Nao, chlorine becomes Claire.
Correct. After gaining an electron, the chlorine atom, with its 17 protons but now 18 electrons, acquires a unit negative charge, forming a chloride anion, Cleo. Now, you have a positively charged sodium ion and negatively charged chloride ion. What happens next? Simple physics.
Opposites attract.
Exactly. Being oppositely charged, these ions powerfully attract each other through strong electrostatic forces. Think magnets, but on an atomic scale. These strong forces form what we call an ionic bond, and the result is the formation of sodium chloride, NaCl, common table salt. Now, a crucial point to remember for your exams. Sodium chloride does not exist as individual, discrete NaCl molecules. Instead, it forms a vast, highly organized crystal lattice structure. It's a large aggregate of these oppositely charged ions, Na, U, and Clo, held together in a repeating pattern by these powerful electrostatic bonds. Let's quickly consider one more example. The formation of magnesium chloride, NgCl. Magnesium Mg, atomic number 12, configuration 282. What does it need to do for stability?
Lose 2 electrons to get to 2, 8.
Right, it loses 2 electrons to form a magnesium chlorocation, Mu, 2 positive charges. Chlorine, as we just discussed, needs only 1 electron, Clu. So to balance the 2 electrons lost by magnesium, how many chlorine atoms are required?
2, 1 for each electron.
Perfect. Magnesium donates 1 electron to each of 2 chlorine atoms. So the overall process is MgO, MgO plus 2A, and then 2Cl plus 2A, Mu plus O. The resulting compound is MgO, magnesium chloride, held together by ionic bonds between MgO and clay ions. So to summarize this section, compounds formed in this manner, specifically by the complete transfer of electrons from a metal, which typically loses electrons to form positive compounds, to a non-metal, which typically gains electrons to form negative anions, are called ionic compounds or sometimes electrovalent compounds. Understanding this elegant electron transfer mechanism is absolutely fundamental to comprehending all the unique properties that these compounds exhibit, which we'll look at next. Okay, now that we have a clear picture of how ionic compounds form through this transfer of electrons, let's turn our attention to their general properties. These characteristics are frequently tested both in theoretical questions asking why they have these properties and in application-based problems. Grasping the why behind each property is crucial for your exams. First, let's consider their physical nature. Ionic compounds are typically solids at room temperature, and they are generally quite hard.
Okay. Because of the strong bond.
Exactly. This hardness isn't a coincidence. It's a direct consequence of the incredibly strong electrostatic forces of attraction holding those positive and negative ions together within their rigid crystal lattice structure. Imagine a tightly packed three-dimensional arrangement of opposite charges. Breaking that structure requires significant force. However, despite their hardness, ionic compounds are generally brittle.
Brittle. So they break easily if hit.
Yes. This means that if you apply pressure, say, hit them with a hammer, they tend to fracture and break into pieces rather than bending or deforming like a metal would. This happens because if you apply force and shift the layers of ions slightly, you might bring ions of the same charge next to each other. Like charges repel strongly, causing the crystal to shatter along specific planes. Next, we look at their melting and boiling points. Ionic compounds possess remarkably high melting and boiling points, very high.
Also because of the strong bonds.
Absolutely. It's the same underlying reason. A considerable amount of energy, specifically thermal energy, is required to overcome or break these powerful interionic electrostatic forces. You need enough heat energy to allow the ions to move freely, transitioning from the fixed solid lattice to a mobile liquid state, melting, or from the liquid to the gaseous state, boiling. Think of common table salt, NaCl. Its melting point is around 801 degrees C, over 1,000 Kelvin, and its boiling point is over 1,400 degrees C, over 1,600 Kelvin.
That's really high compared to, say, water.
Immensely high. Water boils at just 100 degrees C, 373 Kelvin. This huge energy requirement truly underscores the incredible strength of ionic bonds. Now, for solubility, electrovalent compounds or ionic compounds are generally soluble in water.
Why water specifically?
Good question. Water is a polar solvent. Its molecules have a slight positive end and a slight negative end. These polar water molecules can effectively surround and interact with the charged ions, positive cations and negative anions, in the ionic lattice. They pull the ions apart and keep them separated, allowing the compound to dissolve. It's a process called hydration. However, ionic compounds are typically insoluble in organic solvents like kerosene, petrol, ether, benzene, etc. These solvents are generally nonpolar. Their molecules don't have charged ends, so they can't effectively interact with and separate the ions. This difference in solubility is a key characteristic. Finally, and this is a very, very important concept for competitive exams, let's discuss the conduction of electricity in ionic compounds. This comes up again and again. Remember, the fundamental mechanism of electricity conduction involves the movement of charged particles. Now think about ionic compounds in the solid state. Do they conduct electricity?
The ions are fixed, so maybe not.
Exactly right. Ionic compounds in the solid state do not conduct electricity. This is a critical point to remember. The reason, as you said, is that in their solid state, the ions, the charged particles, are held tightly in fixed positions within that rigid crystal lattice. They are not free to move around. And without the movement of charged particles, electricity simply cannot be conducted. However, ionic compounds do conduct electricity in the molten state.
Molten. So when they are melted into a liquid.
Yes. When an ionic compound is heated to its high melting point and becomes a liquid, those strong electrostatic forces holding the ions fixed are overcome by the heat energy. This liberation allows the ions to become mobile, to move freely throughout the molten mass. Since you now have moving charged particles, ions, the molten ionic compound can conduct electricity. Similarly, a solution of an ionic compound in water, an aqueous solution, also conducts electricity.
Because the ions are free in the water.
Precisely. When an ionic compound dissolves in water, it dissociates, breaking up into its constituent ions, mercurians and anions. These ions become free-moving within the solution. When you pass an electric current through the solution using electrodes, these free ions can move towards the oppositely charged electrodes, carrying charge and thus conducting electricity. So the key takeaway, ionic compounds conduct electricity when molten or dissolved in water. Ions are mobile, but not in the solid state. Ions are fixed. Understanding this state-dependent conductivity is vital for various conceptual questions. It's a recurring theme in exams. Okay, understanding the properties of metals and how they form compounds is one thing, but how do we actually get these incredibly useful materials from the earth for our daily use? How do we go from rocks to, say, an iron nail or an aluminum can? This brings us to the fascinating and industrially vital field of metallurgy. This is a key area for questions on large-scale industrial processes in your exams. Let's start with the occurrence of metals. Where do we find them? The Earth's crust is, of course, the primary source of most metals. They exist within the rocks and soil. Additionally, seawater contains various dissolved soluble salts, like sodium chloride, common salt, and magnesium chloride, offering another reservoir, especially for reactive metals like nannan and zor. Now, elements or compounds that are found naturally occurring in the Earth's crust are broadly known as minerals. Lots of minerals exist. However, from an economic and practical standpoint, not all minerals are created equal. Minerals from which a metal can be profitably and conveniently extracted because they contain a sufficiently high percentage of that particular metal are specifically called ores.
So all ores are minerals, but not all minerals are ores.
Exactly. An ore is a commercially viable mineral source for a metal. This distinction between a general mineral and a valuable ore is important. Now, our understanding of the reactivity series directly correlates with how metals occur in nature. It's a beautiful connection. Think about the least reactive metals at the bottom of the series: gold, Au, silver, Ag, platinum, Pt, and often copper, Cu. They are so unreactive.
So they don't combine easily, found pure?
Often, yes. They are frequently found in the free or native state in nature as nuggets or flakes of pure metal. Copper and silver, being slightly more reactive than gold and platinum, can also be found in combined states, typically as sulfide, like Qs or oxide ores. Now consider the most reactive metals at the top of the series: potassium, K, sodium, Nerea, calcium, Ca, magnesium, Mg, aluminium, Al. They are extremely reactive.
So they must be combined, never found free.
Correct. They are never found in nature as free, uncombined elements. They always exist tightly bonded within compound forms in various minerals like chlorides, carbonates, oxides, silicates, and the moderately reactive metals in the middle of the series: zinc, Zn, iron, F, lead, Pb, etc. Where do you think they fit?
Probably combined, but maybe easier to break down than the top ones.
Good thinking. They're generally found mainly as oxides, sulfides, or carbonates. You'll often find that the ores of many metals are oxides. Any idea why oxides are so common?
Oxygen is everywhere.
In the air.
Exactly. Oxygen is a very reactive element and also incredibly abundant in the Earth's crust and atmosphere. It readily combines with many metals over geological timescales, forming stable oxide ores. So based on this natural reactivity, metals are broadly grouped into three categories for extraction purposes: metals of low reactivity, metals of medium reactivity, and metals of high reactivity. And each category, as you'll see, demands very different and specific extraction techniques. These techniques collectively form the fascinating process of metallurgy. So metals are either found free or in compounds, depending on their reactivity. That makes a lot of sense. What are the general steps involved in actually getting the pure metal from its ore once we've found it? Is there a standard process?
Great question. Yes, metallurgy is indeed a systematic journey. It involves several key stages, from the initial mining of the ore right through to finally obtaining the pure metal ready for use. There are generally three primary stages involved in the steps in metal extraction, metallurgy. You might see this illustrated in diagrams, like Figure 3.70 in the NCERT textbook. The first crucial step after mining is the concentration of ore. This is sometimes called enrichment of ore or dressing. Ores, when dug out from the earth, are almost always contaminated with significant amounts of unwanted impurities, things like soil, sand, rocks, clay.
The unwanted stuff.
Right. These earthly or rocky impurities are collectively known as gangue, pronounced gang.
Gang.
Before we can even begin to extract the actual metal compound, these gangue impurities must be removed as much as possible. The techniques used for concentration vary widely. They are chosen specifically based on the differences in physical or chemical properties between the desired ore mineral and the unwanted gangue. For example, some methods might exploit differences in density using washing with water, hydraulic washing, or magnetic properties for magnetic ores, magnetic separation, or maybe differences in how they are wetted by oil and water, froth flotation, used often for sulfide ores. The goal is always to increase the percentage of the desired metal compound. The second major step is the actual extraction of the metal from the concentrated ore. This is where we chemically process the concentrated ore to convert the metal compound into the crude, impure metal. And as we just discussed, the specific chemical method used here is highly dependent on the metal's position in the reactivity series. Low, medium, and high reactivity metals each demand distinct chemical approaches for their reduction. We'll get into those specifics. And finally, the third main step is the refining of the metal, purification. The metal obtained after the extraction step, the crude metal, is rarely in its perfectly pure form. It invariably contains residual impurities, maybe other metals, nonmetals like carbon or leftover reactants. These impurities need to be removed to obtain a metal of high purity suitable for various commercial or industrial applications. This final purification process is what we call refining. So the sequence is concentration right, extraction, refining. We'll delve into the specifics of each of these stages now, looking at the fascinating chemistry involved. All right, let's now dive into the specific extraction techniques for each category of metals based directly on their reactivity. This is core metallurgy content. First, we have extracting metals low in the activity series. These are the ones near the bottom, like mercury, Hg, and copper, Cu, though copper can sometimes be middle reactivity depending on the ore. These metals are characterized by being very unreactive. They don't like forming strong bonds.
They're easier to extract.
Relatively speaking, yes. Because they are so reluctant to form strong bonds with other elements, their oxides can often be reduced to pure metals by simple heating alone. No strong reducing agent needed. This makes their extraction relatively straightforward compared to their more reactive counterparts. Let's take mercury as a prime example. Its common ore is cinnabar, which is mercuric sulfide, HGS. It's a red mineral. When cinnabar HGS is heated strongly in air, a process called roasting, it first reacts with oxygen and converts into mercuric oxide, HGO, releasing sulfur dioxide gas. The reaction is 2 HGSs plus 3 HGO plus 2 SOGO. Then, on further heating, this mercuric oxide, HGO, simply decomposes. It breaks down directly into liquid mercury Hg and oxygen gas. Reaction 2HGOS, 2HGl plus OG. Just heat does the job. This is elegant.
So heat the sulfide, it becomes oxide. Heat the oxide, it becomes metal.
Exactly. For mercury, it's that simple due to its low reactivity. Similarly, copper can sometimes be obtained from its sulfide ore, copper I sulfide, Q-Euro, also known as copper glance. When copper sulfide is heated in air, roasting, it initially forms copper I oxide, QO, and SO. Reaction, 2 euros plus 3 euros plus 3 euros plus 2 SO euro. Now, if you control the conditions, this copper I oxide can then react with any remaining unreacted copper I sulfide in the mixture upon further heating without air. And this reaction produces molten copper metal, Cu, and sulfur dioxide gas, SO euro. Reaction, 2 euros plus QO0 plus SAO plus SO euro. Notice here, the copper sulfide itself acts as a reducing agent for the copper oxide. This is called auto-reduction or self-reduction, again, demonstrating how these unreactive metals can be obtained with minimal chemical intervention, sometimes just by carefully heating their ores. Okay, now let's move up the reactivity series to extracting metals in the middle of the activity series. This group includes important metals like zinc, Zn, iron, Fe, lead, Pb, and sometimes copper, Cu, when found as carbonate or different oxide ores. These metals are moderately reactive. In nature, as we said, they are typically found as sulfide ores or carbonate ores.
And oxides are easier to reduce.
Exactly. It's universally recognized in metallurgy that it's much easier to obtain a metal from its oxide form compared to its sulfide or carbonate form. Therefore, a crucial preparatory step before the actual reduction to metal is to convert these sulfide and carbonate ores into their respective metal oxides. This conversion is key. For sulfide ores, the process used is called roasting. Remember this term. Roasting involves heating the sulfide ore strongly in the presence of excess air, oxygen. For instance, if you have zinc sulfide ore, ZnS, zinc blend. Roasting vigorously converts it to zinc oxide ZnO, releasing sulfur dioxide gas reaction. 2ZnS plus 3OO, 2ZnO plus 2SO. The azero often needs to be captured to prevent pollution.
Roasting. Sulfide plus excess hair oxide plus SO heroes.
For carbonate ores, the process used is called calcination, another key term. Calcination involves heating the carbonate ore strongly, but this time in limited air or even in the absence of air. Taking zinc carbonate, ZnCO, calamine as an example, calcination simply decomposes it into zinc oxide, ZnO, releasing carbon dioxide gas reaction. ZnTNO plus KOG, no air needed, just heat to break it down.
Calcination. Carbonate plus limited no air oxide plus KO yours. Got it. Roasting for S, calcination for C.
Right. So once the metal sulfides and carbonates are converted to metal oxides, like ZnO from either ZnS or ZnCO, these metal oxides are then reduced to the corresponding metals. How? The most common and economical method involves using a suitable reducing agent. And the workhorse reducing agent in metallurgy is carbon, usually in the form of coke, which is mostly carbon.
Using carbon to pull the oxygen away.
Precisely. When zinc oxide, ZnO for instance, is heated strongly with carbon, coke, the carbon pulls the oxygen away from the zinc. This reduces the zinc oxide to metallic zinc, which is often vaporized at the high temperatures required and then condensed. Carbon itself gets oxidized, usually to carbon monoxide CO reaction, ZnO plus CS, ZnG plus COG. This is a classic example of reduction using carbon. It's used extensively for iron extraction smelting in a blast furnace as well. Now, besides carbon, sometimes displacement reactions using more reactive metals are employed as reducing agents. This is usually when carbon isn't effective enough or for specific applications. Highly reactive metals like sodium, calcium, or especially aluminium can act as very strong reducing agents.
Because they are higher up in the reactivity series.
Exactly. They have a much stronger affinity for oxygen than the metal in the oxide we're trying to reduce, so they can displace the less reactive metal from its oxide. For example, manganese dioxide, MnO, can be reduced by heating it with aluminium powder. A vigorous reaction takes place. Aluminium displaces manganese, 3MnO gyros plus 4As plus 2L-arrow plus heat. Notice the manganese is produced in liquid form.
Because the reaction is very hot.
Very, very hot. These displacement reactions using reactive metals like aluminium are often highly exothermic. They release a tremendous amount of heat. The amount of heat evolved can be so large that the metal being produced is actually formed in the molten state, as we saw with manganese. A prime example of this, and one that's incredibly important for practical applications and frequently asked about in competitive exams, is the thermit reaction. Heard of it?
Thermit, yes. Used for welding railway tracks, right?
That's the one. It involves the reaction of iron oxide, essentially rust with aluminium powder, reaction, FeRASS plus 2L plus AlOUS plus lots of heat. The iron produced is so incredibly hot, temperatures can exceed 2000 degrees C, that it's in a molten state. This molten iron is then directed into the gap between broken railway tracks or used to repair cracked machine parts. It fuses the pieces together as it cools and solidifies. It's an almost spectacular welding technique based entirely on a displacement reaction.
The thermit reaction sounds incredible, Tudor, like controlled fireworks with a purpose. So for the most reactive metals, the ones right at the very top of the series, like sodium, potassium, calcium, aluminium, you mentioned we can't just use carbon. Why not again? And what special method is employed for them? Does it get even more complicated?
Excellent point, and you've remembered the key distinction correctly. For these most reactive metals at the top of the activity series, Na, K, Ca, Mg, alcarbon is simply not a strong enough reducing agent. Why? Because these metals themselves have a much higher affinity, a stronger desire for oxygen than carbon does. Carbon just can't pull the oxygen away from them effectively. It loses the tug of war for oxygen.
Okay, so carbon isn't strong enough. What works then?
For these highly reactive metals, we have to resort to a more powerful, though often more energy-intensive method, electrolytic reduction. This uses electricity to force the reduction. It's a slightly different ballgame, yes, involving electrochemistry. In this process, the metals are typically obtained by the electrolysis of their molten fused salts, usually chlorides or sometimes oxides. We can't use aqueous solutions here, why not?
If water is present, would the water react instead? Since these metals are so reactive with water.
Exactly. If you try to electrolyze an aqueous solution of, say, NaCl, you'd get hydrogen gas produced at the cathode from the water reduction, not sodium metal, because sodium is more reactive than hydrogen. So we must use the molten salt with no water present. Let's take sodium extraction from molten sodium chloride, NaCl, as the classic example of Down's process. We pass a strong electric current through the molten NaCl. At the cathode, the negatively charged electrode, the positively charged sodium ions, not ore, from the molten salt are attracted. They gain electrons, reduction happens at the cathode, and are deposited as neutral liquid sodium metal. Reaction, Na plus E, like an A plus EO. At the anode, the positively charged electrode, the negatively charged chloride ions, all Kobe, are attracted. They lose electrons, oxidation happens at the anode, and are liberated as chlorine gas, HCO. Reaction, 2 clay molten Eg plus 2L. This precise electrolytic method is used to obtain metals like sodium, potassium, calcium, and magnesium from their molten chlorides. Aluminium extraction is slightly different. It's obtained by the electrolytic reduction of molten aluminium oxide, or LiORO, dissolved in a molten cryolite, now LiORO. The cryolite lowers the melting point and increases conductivity, Hall-Héroult process. But the principle is the same, reduction at the cathode using electricity. This method is energy intensive, requires a lot of electricity, which is why aluminium production plants are often located near hydroelectric power sources. But it's absolutely essential for extracting these very reactive and commercially important metals. Right, so we've covered extraction, simple heating for the least reactive, carbon deduction usually for the middle ones, and electrolysis for the most reactive. Now, the metals obtained from any of these reduction processes, the crude metal, are rarely perfectly pure. They still contain various residual impurities. These could be unreacted or other metals that were present in the ore, nonmetals like carbon, especially if carbon reduction was used, dissolved gases, etc. To get those truly pure metals needed for high-tech applications or specific uses, we need to refine them. We need that final purification step. The most widely used and often most effective method for refining many impure metals is electrolytic refining. This process is incredibly versatile and is commonly used for refining metals like copper, zinc, tin, nickel, silver, gold, lead, and even aluminium. It's a key concept for your board exams and competitive tests. Let's understand the process using copper refining as the classic, most commonly depicted example. Imagine setting up an electrolytic cell, anode. The impure metal in this case, a thick block of the crude impure copper obtained from extraction, is made the anode. This is connected to the positive terminal of the power supply.
Anode, impure metal.
Yep. Cathode. A thin strip of very pure metal, pure copper in this case, is made the cathode. This is connected to the negative terminal.
Cathode, pure metal strip.
Electrolyte. A solution of a soluble salt of the metal being refined is used as the electrolyte. For copper refining, this would typically be an aqueous solution of copper sulfate, CuSO, usually acidified slightly with sulfuric acid to improve conductivity.
Electrolyte, solution of the metal salt, like CuSO.
Now, the mechanism works beautifully like this. When you pass an electric current through the electrolyte, 1. At the anode, impure copper, the pure copper atoms lose electrons and dissolve into the electrolyte as positive copper ions. Reaction. Q, impure, plus 2U, the anode gradually gets eaten away. 2. These Q ions move through the solution towards the cathode, pure copper strip. 3. At the cathode, the Q ions from the solution gain electrons and are deposited as neutral, pure copper metal atoms onto the cathode. Reaction. The pure cathode strip gradually gets thicker, so it's essentially a transfer of pure copper from the impure anode through the solution onto the pure cathode. Now, what happens to the impurity fate? This is where it gets interesting, especially for competitive exams. More reactive impurities present in the impure anode, like zinc or iron, if they were there, also dissolve into the electrolyte as ions, but they generally stay in solution because they are harder to reduce than copper ions. Less reactive impurities present in the impure anode, like silver, gold, platinum, if they were present in the original ore, do not dissolve. As the copper around them dissolves away, these insoluble impurities simply fall off the anode and settle down at the bottom of the electrolytic cell as a sludge.
Sludge at the bottom.
Yes, and this sludge is famously known as anode mud or anode sludge.
Anode mud. Is it important?
Very much so, economically. This anode mud often contains valuable precious metals like silver, gold, and platinum, which were present as impurities in the copper ore. These can then be recovered separately from the mud, adding significant extra value and profitability to the copper refining process. This detail about recovering precious metals from anode mud is a favorite point for competitive exam questions, so make a note of it. Okay, so we've extracted and refined our metals. They're incredibly useful, durable materials, but they are susceptible to a natural process that slowly degrades them over time: corrosion. This is a very important concept. Touching upon environmental chemistry, economics, corrosion causes huge losses, and practical applications in our daily lives. Corrosion, in general terms, is defined as the process where the surface of some metals is slowly eaten away or degraded when exposed to certain environmental factors, typically moist air, water, acids, or other chemicals for a prolonged period. It's essentially the metal reacting undesirably with its surroundings, losing its strength, appearance, and other desired properties. It's often an oxidation process. Let's look at some common examples you've likely observed. Silver. Ag. When silver articles, like jewelry or cutlery, are exposed to air over time, they lose their bright shine and turn black or tarnished.
Yes, silverware goes black.
That happens because silver reacts with small amounts of sulfur compounds, like hydrogen sulfide, H0, present in the air, forming a black coating of silver sulfide, ADUS. Copper articles, initially shiny and reddish-brown, slowly lose their luster and develop a distinct green coat when exposed to moist air containing carbon dioxide.
Like on old copper roofs or statues.
Exactly. That green substance is identified as basic copper carbonate, a mixture roughly KuCa-OH. Iron Fe rusting. This is perhaps the most well-known and economically damaging example of corrosion. When iron or steel is exposed to moist air for a prolonged period, it acquires a coating of a reddish-brown, flaky substance. This substance is called rust, and the entire process is known as rusting. Rust is hydrated iron oxide, roughly FeOKO. Now, the conditions necessary for the rusting of iron are crucial for your understanding and are very frequently tested, often with diagrams based on a classic experiment, like Activity 3.14 in NCERT. Imagine setting up 3 test tubes, each containing a clean iron nail. Tube A contains the iron nail, some water, and is open to the air, so the nail is exposed to both air, oxygen, and water. Tube B contains the iron nail immersed in boiled distilled water to remove dissolved air, with a layer of oil floated on top to prevent fresh air from dissolving in. So the nail has water, but essentially no air. Tube C contains the iron nail and an anhydrous drying agent like calcium chloride to absorb all moisture, and the tube is stoppered. So the nail has air, but no water, moisture. After a few days, what do you observe?
Only the nail in tube A rusts, the one with both air and water.
Precisely. The nail in tube A rusts significantly. The nails in tube B, water only, and tube C, air only, show negligible or no rusting. This experiment conclusively proves that rusting of iron requires the simultaneous presence of both air, specifically oxygen, and water, moisture. If either one is absent, iron will not rust or will rust extremely slowly. It's a key takeaway.
So rust needs both air and water. That's very clear from the experiment. How can we protect valuable iron articles from rusting, given how common and damaging it is? Are there practical solutions we use every day?
Excellent question. Preventing corrosion, especially the rusting of iron, which forms the backbone of so much infrastructure and machinery, is a huge industrial and domestic concern. It costs economies billions every year. Fortunately, there are several very effective methods for the prevention of corrosion. Common methods include some fairly simple barrier methods. Painting the metal surface creates a physical barrier between the iron and the environment. Applying oil or grease does the same, often used for moving parts of machinery. Chrome plating or nickel plating provides a hard, shiny, protective, and decorative layer. Anodizing, which we discussed earlier for aluminium, creates a thick, protective oxide layer. And perhaps one of the most impactful and versatile solutions is making alloys. We'll come back to that. But first, let's focus on galvanization. This is a very widely used and important method specifically for protecting steel and iron from rusting. It involves coating the iron or steel object with a thin layer of zinc metal. You often see galvanized buckets, pipes, roofing sheets.
Why zinc specifically?
That's the clever part. The key advantage of galvanization, and this is a concept frequently tested, is that the galvanized article is protected against rusting even if the zinc coating gets scratched or broken.
Even if it's broken. How does that work?
It works because of the Reactivity Series. Remember where zinc and iron are? Zinc is more reactive than iron. So if the coating is scratched and both zinc and iron are exposed to air and moisture, the more reactive zinc will corrode preferentially. The zinc essentially sacrifices itself to protect the iron. It gets oxidized instead of the iron. This is often referred to as sacrificial protection. It's a brilliant piece of applied chemistry. Now, back to alloying. This is another extremely effective method, not just for preventing corrosion, but also for improving many other properties of metals like hardness, strength, or even lowering melting points. An alloy is defined as a homogeneous mixture of 2 or more metals, or sometimes a metal and a nonmetal. The components are melted together and then allowed to cool.
Like mixing ingredients for a better result.
Exactly. An alloy is prepared by first melting the primary metal, the base metal, then dissolving the other elements, metals or nonmetals, into it in definite, precise proportions, and finally cooling the homogeneous molten mixture to solidify. This process allows us to engineer materials with specific desired properties that the pure constituent metals might not possess on their own. Let's look at some striking examples of improved properties through alloying, especially related to iron. Iron, pure. Pure iron on its own is actually quite soft and tends to stretch easily, especially when hot. This makes it unsuitable for many structural applications where strength is needed. Steel. If you mix pure iron with just a small amount of carbon, typically less than 1.5%, often around 0.05% to 1%, the resulting alloy is steel. Steel is significantly harder and much stronger than pure iron. This transformation is why steel, not pure iron, is the backbone of modern construction and engineering. Stainless steel. For ultimate rust resistance, iron is alloyed with other metals, primarily nickel and chromium. This forms stainless steel. It's not only hard and strong like other steels, but crucially, it does not rust under normal conditions. This makes it ideal for cutlery, surgical instruments, kitchen sinks, cookware, chemical plants, anywhere. Corrosion resistance is vital, a true marvel of material science. There are many other important alloy examples you should definitely know for your exams. Brass, an alloy of copper and zinc, Q plus Zn, widely used for decorative items, screws, musical instruments. It's harder than pure copper, but not as good an electrical conductor. Bronze, an alloy of copper and tin, Q plus Sen, famous from the Bronze Age. It's harder than brass and was used for statues, bells, and historically, weapons. Also not as good a conductor as pure copper. Solder. This is a crucial alloy usually made of lead and tin, Pb plus Sen. Its key property is a very low melting point. This makes it absolutely ideal for joining electrical wires together in electronics and plumbing. It melts easily and solidifies quickly to form a conductive joint.
Solder for electronics, right?
Gold jewelry. Pure gold is known as 24-karat gold. But as we mentioned, it's very soft and malleable, almost like butter. Unsuitable for durable jewelry. To make it harder and more resilient for ornaments, it's alloyed with other metals, usually copper or silver. In India, 22-karat gold is very common. What does 22 karat mean?
22 parts gold out of 24 total parts.
Exactly. It means 22 parts of pure gold are alloyed with 2 parts of another metal, like copper or silver or a mix. This provides the necessary hardness for jewelry without significantly reducing its preciousness or altering its color too much. Amalgam. Any alloy where one of the constituent metals is mercury, Hg, is called an amalgam. A common example historically was dental amalgam, an alloy of mercury with silver, tin, and copper, once widely used for filling tooth cavities. And finally, speaking of alloys and corrosion resistance, a truly remarkable testament to ancient Indian metallurgy is the iron pillar at Delhi, located near the Qutub Minar. Built over 1,600 years ago, this massive pillar, standing 8 meters high and weighing over 6 tons, remains remarkably rust-resistant to this day, despite being exposed to the elements for centuries.
The 1,600 years of no rust.
It's still debated, but scientific analysis suggests it's due to a combination of factors. The high purity of the iron used, the presence of a high phosphorus content, which helps form a protective passive film, the unique forging techniques used by the ancient Indian iron workers, and possibly environmental factors. It's an ancient masterclass in metallurgy, showing incredible skill in corrosion prevention centuries ago, a truly remarkable nugget of history and science combined. So there we have it. We've completed our comprehensive deep dive into metals and nonmetals. We systematically covered their distinguishing physical and chemical properties. We understood the fundamental why behind their reactions by exploring electron configurations and ionic compound formation. We dissected the incredibly important Reactivity Series, which predicts so much about their behavior. We then ventured into the intricate processes of metallurgy covering occurrence, extraction based on reactivity, heating, carbon reduction, electrolysis, and finally, refining. And of course, we rounded it all off by looking at corrosion, that universal challenge, and its various practical prevention methods like galvanization and alloying. It's quite a journey through this chapter.
Thank you so much, Tutor. That was incredibly detailed and really clear. I feel much more confident now, especially with all the exceptions, the nuances of reactivity, those specific reactions like the Thermit reaction, and how it all ties back to the Reactivity Series and electron structure. It connects much better now.
You're most welcome. I'm glad it helped clarify things. Remember, the absolute key to mastering this chapter for your upcoming exams is not just understanding it now, but consistent active recall and diligent practice. Repetition is key. Let's just quickly summarize the absolute key takeaways one last time, bullet point style for your notes. Elements are classified as metals, nonmetals based on physical properties, lustre, malleability, ductility, conductivity, sonority, hardness. But always remember the crucial exceptions, like alkali metal softness, mercury state, gallium cesium melting points, iodine's luster, graphite's conductivity.
Yeah.
They love testing exceptions.
Right. Exceptions are key.
Chemically, metals tend to lose electrons, formations. Form basic oxides. Remember the special amphoteric oxides, era. Non-metals tend to gain electrons, form anions, form acidic or neutral oxides. The reactivity series is paramount. Memorize it. It predicts reactions with O, acids, and displacement reactions. Metals above H displace H from dilute acids, except HNO, unless it's MgMN with very dilute HNO. Higher metals displace lower metals from salts.
Reactivity series is central. Got it.
Ionic compounds, formed by electron transfer, metal to nonmetal. Result: strong electrostatic forces leading to distinct properties. Solid, hard, brittle, very high mpBp, generally soluble in water, conduct electricity only when molten or in aqueous solution. Mobile ions, not as solids. Fixed ions. This conductivity point is vital. Metallurgy, the process. Ore concentration, remove gang. Extraction, based on reactivity. Simple heating for low, roasting calcination, then usually carbon reduction for medium, electrolysis for high. Refining, usually electrolytic refining. Remember, anode mud contains valuable impurities.
Concentration, extraction, refining, based on reactivity.
Corrosion, degradation of metals. Rusting of iron. Rusting needs both oxygen and water. Prevention methods: painting, oiling, galvanization, sacrificial protection by zinc. Alloying, for example, steel, stainless steel. Remember the Delhi iron pillar example. Okay, so for your next step, what should you do? Make sure to revise all these points thoroughly. Go back through your notes, maybe replay parts of this discussion. Then practice the past year questions based on this chapter diligently. Focus especially on the conceptual questions about the reactivity series, ionic bond formation, properties of ionic compounds, and the different extraction methods. Why use electrolysis here? Why carbon there? Ruse. And definitely solve all the NCERT exercises related to this chapter. They cover the fundamentals well. If you encounter any doubts on this chapter while practicing any question, big or small, please do not hesitate to reach out. Ask questions. Keep up the excellent work. You're building a strong foundation.